start with this. Cataclasis from viscous flow. This is actually the title I decided to present here. But with also experiments I did 2 days before coming here, I wanted to be a little bit more aggressive towards the end, maybe remove the carbonate-hosted faults and be more generic to see a little bit the big picture. But weakening along faults, we have seen it in the nice introduction today and the other days too. Why is it important? Because during the ruptures, during earthquakes, the rupture tip propagates at very fast speed, and it is fed by a stress transfer that comes from the whole fault. And this process is enhanced if the fault itself has a low friction coefficient because it's sliding at a lower velocity, and need to transfer the stress towards the tip to render the mechanism more efficient. In order to do that, along the fault there are thermally activated mechanisms that reduce the fault strength by dynamic weakening, what is called dynamic weakening. As shown in the previous presentation, we have this nice graph that comprises many different experiments that all show that at high velocity the friction coefficient is reduced, but every single experiment done with different material needs a different explanation. So we have different weakening mechanisms, each with its own physical characterization, more or less empirical. And some of them were really recent. For example, the diffusion-assisted grain boundary sliding that has been hypothesized to work, for example, in calcite or in carbonates in general. This is the focus of the first part of the presentation. And so let's investigate the calcite. We do experiments on the rotary machine. That is the classic squeezes your rock in an uniaxial direction and starts shearing it with the rotation of the upper cylinder. And here I show just the experiments done with the maximum normal stress we can achieve, 25 megapascals normal stress, and high velocity, 1.4 meters per second. What you obtain out of this machine, the mechanical data, is a nice weakening curve that you all recognize, that works more or less for all materials. In calcite, it's quite nice to see because it has 4 distinct stages that we observe. So let's just observe the evolution of friction coefficient with displacement. You have slip hardening, first stage 1, rapid drop of friction coefficient during stage 2, a sort of slowly evolving condition where the friction coefficient remains low, and a 4th stage when you re-strengthen. This happens always when the machine decelerates to stop. And these are 4 experiments stopped at different displacements that I used to investigate the evolution of microstructure. You see that they plot on top of each other, so there is a nice reproducibility. The temperature, of course, rises most when the friction coefficient is high, then becomes lower and lower and drops during the deceleration phase. Microstructures, we recover the sample after each experiment, and you already see that the sample shows the nice reflecting surface that it's seen pretty much every material shared at this high velocities. But our focus was not on the mirrors as usual, as is usually done, but we try to recover the full sandwich, and it has been a game changer for my project because we try to recover from top to bottom what is the whole architecture of the principal slip zone, not just what is believed to be a slip zone itself. So we cut like in a parallel to the velocity vector, and we explore it with at the electron microscope. This is what you obtain. Again, we see this is the indentation of the lower cylinder, and this is the indentation of the top cylinder. And more or less, I managed to recover all of the stages. From stage 1, we have the characteristic architecture of widespread cataclastic deformation and a very well localized principal slip zone that is still cataclastic. And that localizes almost immediately at the beginning of the experiment, just after a few millimeters of slip. Then we see the progressive evolution of this principal slip zone into something different. Stage 2, just after the weakening, it still seems cataclastic but has sharp boundaries, and even sharper when you reach stage 3, and stays always the same, bounding between 2 straight boundaries. It will be more clear in the next slides. And during stage 4, you have a brittle overprint on your principal slip zone. But what we are interested in here, I keep forgetting this, is we want to zoom out into the principal slip zone comprised between 2 these two flat boundaries that are represented by the mirrors when you open the sample. And zooming in, this is the texture. So the formation of the principal zip zone is in a volume, even during the dynamic weakening. And this it's in a principal zip zone that has a finite thickness. And this thickness is pretty much homogeneous throughout the sample. And inside you see a small grain size, and a particular texture is quite resembling that of natural ultraminorites that are seen in the ductile regime, not in the brittle regime. And is characterized by triple junctions, homogeneous grain fairly homogeneous grain size, and an oblique foliation. And the porosity is very low when it's in the TEM. Now, with this texture, and that is closely resembled the ultraminorites, we try to hypothesize that probably, since the grain size is much bigger outside, it can be controlled by grain size sensitive creep. And but this is just a textural evidence. And with this, we provide an initial conceptual model where the weakening is reached when a critical temperature is reached, but it also prepared by the initial stages of localization that produces a small grain size. So ignore the model for now, we make the long story short. We have a transition from brittle cataclasis, prepares a principal slip zone where you build up the temperature, and becomes gradually more viscous when the temperature increases, and you reduce its viscosity, and it turns into a macroscopic friction coefficient. And stage 4, embrittlement, back again when the conditions go away of temperature drops and you slow down. You go away from the viscous flow and you go back to brittle regime again. But are you convinced that this is actually a viscous flow? We need more independent evidence. One way to do it is by using acoustic emissions on the apparatus. So we have designed a small sample holder called the Hexapus that hosts some piezoelectric acoustic sensors that measure the vibrations coming out, the acoustic emissions coming from the sample. And what you obtain is a raw data, voltage against time, that can be analyzed using the fast Fourier transform, analyzing basically the spectrum that is inside each part of the experiment. You can visualize it pretty well using the spectrogram. Spectrogram is quite simple. After fast Fourier transform, you obtain a frequency with this relative intensity that is represented from blue to yellow, higher intensity going toward you in time. You already see that, this will be the experiment, that you can recognize that the experiment is non-homogeneous. Acoustic emissions have a different style throughout the experiment. And if I plot on the top the mechanical data, I already see that stage 3 is, we can consider it silent compared to the other stages. And we have a lot of acoustic emissions coming out after the end of experiments that is correlated to thermal cracking, enhancing even more what is the brittle overprint and hindering a little bit what is the interpretation of our experiments. So stage 3 is silent compared to the others. And this is typical of something that is flowing viscously, for example, rather than a cataclastic flow. Even more evidence is added when we want to explore further the weakening mechanisms. And a way to do that, again, we've seen in the previous two sessions, even better, is using the EBSD electron backscatter diffraction analysis when we test the orientation of crystals and the intensity of our texture. I will focus more on the stereographic projection because it's more immediate, but we've done also misorientation analysis, orientation maps, and so on, full analysis. And today I will show just what's happening inside the principal zip zone. You can also assess what's happening in the outer layers, and they add more further information, but let's keep it short. So starting from stage 1, mechanical data shows that inside the principal zip zone, there is a sort of CPO, so crystals are slightly oriented, but it's not so intense. This is there is a paper coming out from de Murtas et al. That shows that this is probably due to in cataclastic processes is oriented fracturing and twinning of calcite that provides a slightly lower CPO. It changes completely when we go into stage 2. Stage 2, just after the weakening, CPO bang becomes very strong. Is monocline. You see the repetition of the A-axis, and the C-axis is very well oriented with a strong intensity of your CPO. Then when we go at the beginning of stage 3, when you have the stable principal zip zone with a finite thickness that stays the same, the CPO becomes weaker and even more weaker with a progressive displacement. And this can be compared it cannot be compared to high velocity stuff because it has not been done before, but to low velocity experiments. It's not so dissimilar to what they saw in calcite at much lower strain rates. Here we are talking about strain rates 10 to the 4th compared to strain rates 10 to the -4, for example. And this evolution of the CPO has been interpreted previously like cataclasis. We have a low CPO. Twinning can add a little bit of it. But grain size insensitive creep will orientate your crystal favorably to the stress field. But then, when grain size sensitive creep, like diffusion, kicks in and becomes a viable mechanism to deform your material, becomes weaker and weaker. This has been predicted mathematically by Wheeler, but not really shown. In this case, you can imagine from this stage to this stage, the finest strains are 20,000 and more in that thin principal slip zone. Okay, this was calcite. I tried to convince you that this is actually a myelinite, even at very high strain rates, something that has not been idealized before. But calcite is just one material. Can we expand it to the other materials? Because as we have seen from the previous presentation, this works for a wide range of materials, and they seem to have the same evolution, despite having different weakening mechanisms that are material dependent. Let's try to unify a little bit. So I did, again, well, lack of a general law is a little bit bold, but probably what I want to do here is to unify and try to see if the materials respond the same way. So we do experiments the same way we've done with calcite, but using different materials. In this case, I choose materials that typically don't melt, as seen in the experiments, but belong to different mineralogical classes with different bonds. We have carbonates on top. Calcite, classic one, is easy to use. Anhydrite, sulfates, sodium chloride, halides, and even olivine, but it was 2 days before coming here, so believe me, it shows the same trend you will see after, but I didn't have the time to plot it here. And this is the classic way of representing the experiments, so displacement against friction coefficient. What if we take into account the temperature and the stress rather than the friction coefficient? We plot it in an Arrhenius type, Arrhenius space. This is what you obtain. Basically, the experiment is evolving from right to left with increasing temperature, the inverse of the temperature, and shear stress. And we see, this is just Gabbro from Nielsen in 2008 that already shows a linear relationship that is typical of melts because they show a Arrhenius type relationship. But it works also for stage 3 in experiments done with other materials. For example, this is calcite, the pink one, and can be approximated by just an Arrhenius type relationship where you can find A and B pretty easily. And in calcite, I tried to demonstrate that was a myelinite. And myelinites, we know that depend on temperature in an Arrhenius type fashion. And a melt as well is an Arrhenius type dependency. So we have viscous flow subsolidus and viscous flow supersolidus. And what about the other 3 materials? So let's explore the textures. If we go and do the same stuff that we've done for calcite, again, calcite was that one, principal zip zone finite thickness. The same is dolomite. You can't see it very well because you don't have the big sintering at the borders, but this is a zone of reduced grain size with you can find an oblique foliation, and fortunately it's very difficult to clean, but all of them, and it's very well seen in sodium chloride and anhydrite, it's always a volume that is deforming. And there is a little bit of brittle overprint, as I said before, that might hinder your interpretation, but deformation appears to be in a volume effectively. So where thermal effects can involve different weakening mechanisms, not necessarily strictly dislocation, diffusion creep, or so on, but distributed in a volume with so you can calculate the viscosity. So just a brief recap. So just for what concerns calcite, you can have ultramyelinites, and that deform a very high strain rates, something that was not actually seen before. And the coseismic creep mechanisms that provide the weakening mechanism might not be so different from much lower strain rate myelinites. We just need to explore it at the submicron scale because the grain size there is much, much finer. It's below the micron size. So the kinetic might be different. And if we expand the vision, we see that the materials, independently if it's subsolidus or supersolidus, at least when they are allowed to evolve spontaneously, localizing, they can show an Arrhenius type dependence and have their own viscosity. And that can be the fashion of earthquakes, so being viscous rather than brittle. So thank you for your attention.